For our final video on categorical logic, I wanted to discuss Sorites arguments. A Sorites argument is similar to a categorical syllogism. It's just an extended form of categorical syllogisms. You might even think of it as like a chain of linked categorical syllogisms. The name is derived from the Greek word soros, meaning heap. The method of diagramming that we used for categorical syllogisms is easy to extend to Sorites arguments. It works very well for Sorites arguments. So, a couple of things that we need to know about Sorites arguments is that it is much easier to diagram them if they are put into standard form. It's possible to diagram them without having them in standard form, but it's much easier if they are in standard form. So since the standard form for categorical syllogisms is to have the major premise, which is the one containing the predicate term, come first, and the minor premise, which is the one that contains the subject term, come second, I think that it makes the most sense to have the major premise come first and the minor premise come last for our Sorites arguments. And all premises need to be linked together in a chain by having a term in common with the premise that is above or below it. So this would mean essentially that all of the terms except the subject term and the predicate term are middle terms for the Sorites, and they link the subject term and the predicate term together. So here's an example along with the diagram. All D are G, all B are D, all S are B, all T are S, and then our conclusion says all T are G. Okay, so T is a subclass of G. So if these premises are all true, then it would have to be the case that the conclusion is true. So this argument is valid. And actually, it's very similar to the AA1 or Barbara form. It's really just an extended version of that, but it has the same pattern of reasoning. Now, there's really no limit to the number of premises that you could have. As long as the argument has that form and has that characteristic pattern, it's going to be valid. So here's an example with 10 premises. And this also is going to be valid. Now, one thing that you'll notice is that it has this kind of crisscross pattern here where the subject term in one premise then becomes the predicate term in the next. So you can see that these premises are all linked together in this chain. So as long as it has this form, there's really no limit to the number of premises that you would have, and the conclusion would have to follow as long as the premises are true. Okay, now here's one with a negative premise. So our first premise says no S or D. So that's represented in our diagram as just being two completely separate classes. Our next premise, all O are S, and then all R are O. And then our conclusion says no R are D. Well, that would have to be the case. There's no other way it could be if those premises are true. Because if R is a subclass of S and S does not overlap D, then there's no possible way that R could overlap with D or be a subclass of D. Okay, so here's going to be one more example with using a negative premise. So all P are D, okay, no B are D, all C are B, all S are C, and then our conclusion, no S are P. Okay, and that also is going to have to be valid. Now, when there is a particular premise involved, things get a little more complicated, especially with the Sorites, because there we have to consider both ways of diagramming that particular premise, as well as any possible variations on those two ways of diagramming. So, for example, we have all I are C, all B are I, all U are B, and then some P are U. And our conclusion says some P are C. Well, that's actually going to be correct for this diagram, which shows that that conclusion is possible. However, if we look down at some of these other diagrams, we'll see that some PRC does not necessarily have to follow. So in this case, this diagram is consistent with the premises, but here it's going to be the case that all P are C. And actually in this diagram as well, it's going to be the case that all P are C. So what that shows then is that this conclusion does not necessarily have to follow from the premises, which means that the argument is valid. Now, if you were to say either all P are C or some P are C, then that would be valid, but it's not valid to just say some P are C, because it's possible to get a different conclusion with all of those premises being true. So it's invalid. Okay. Let's actually move down a little bit further. All right, so here's going to be another example. All E or F, all C or E, all D or C, all B or D. Okay, that's true. And then some A are B. So this diagram is consistent with these premises. And then our conclusion says some A are F. Okay, but as you can see from this diagram indicates that actually all A are F. Okay, now we could have this diagram right here. And in this case, it would be true that, let's look back at our conclusion, some A are F. It is possible to have some A or F, but it's also possible that it could be the case that really all A or F. So this argument as well is going to be invalid. And here we see another example where we have some A or F. Okay, so no A or F can be eliminated as a possibility because B is a subclass of F. And so it's also either a subclass of A or overlaps A. But the argument isn't valid because the conclusion does not have to be some A or F. Okay, now this is important because this is different than the Boolean interpretation or Aristotle's. For both of those views, the argument is valid with some A or F as the conclusion. All right, so let's do one more. Suppose that we have this argument. No E are D, all C are D, all B are C. Okay, so that is accurate. And then some A are B. Okay. And then our conclusion says some A are not E. All right, well, it may appear that that conclusion would be correct, but our diagrams show that actually no A are E. So for this particular diagram, that would not be the conclusion that follows. So some A are not E is just another way of saying some A are not E and some A are E, or in other words, some A are E. So for the particular premise, whenever you have some S are P and some S are not P, if you have either one of those, you can use the full statement, some S are P and some S are not P, or you could just use one or the other. In this case, it would have to be the case in order for this particular conclusion to follow. It would have to be the case that some A are E and some A are not E. Okay, so that's not going to be true in this diagram. So this shows that the argument is invalid. Now, it is possible, of course, that you could have some of A overlap E and some of A not overlap E. If we had this diagram down here, then this conclusion would be correct, because this would show that some A are E and some A are not E. But it doesn't have to follow from that. So the fact that we can get the answer of no A or E shows that the argument is invalid. If you'd like to learn more about Sorites arguments and this type of diagramming, you can look at the written document The address where you can be able to download it is listed below.